pressure relief system. And Mrs. Namita Modak is a BTech and an MTech from IIT Kharagpur and presently associated with PMEC Consultants Private Limited as a senior principal process engineer. She has more than 16 years of experience in various sectors like oil and gas, petrochemicals, refinery, and chemical. And she has done a lot of projects in her working time. So now I leave the I request Ms. Lekha Nirmal to take on the session from my side, and in order to talk further, and the session will be conducted by Mrs. Namita Modak. Thank you so much.
Thank you so much. I am audible, right? My voice is clear?
Yeah.
Great. So I'm just sharing my screen. Please let me know once you can see my screen. My screen is visible?
Yes, yes, it is visible.
Great. So good evening, everybody. Thank you so much for coming. I just quickly wanted to give a brief about what we PMEC Consultant do. And then Namita Madam will quickly start with the pressure relief systems. So we PMEC Consultant, we are an engineering, procurement and construction management company. And what we are, why we exist, the source of the organization. So we exist to proactively seek and help people lead a better life. How we achieve that is by providing compassionate care and building capabilities that have a lasting value. Our spiritual foundations or core values are holistic approach, companionship and collaboration, provide solution, not mere engineering, stay united and grow together. So this is something that every member of the PMEC family lives day in and day out. And also this is something that our clients observe and experience when they work with us. The industries that we serve. So we serve oil and gas, both onshore and offshore, refineries, power plants, tank terminals, chemical plants, and also water treatment plants. So we do a variety of works. Now, PMEC Group was formed in 1988, which is almost 33 years ago, with the aim of providing EPCM services that include basic, feed, residual, and detail engineering, also special studies. So basically, we provide an end-to-end engineering solution to all our clients. We are also ISO 9001:2015 certified. Moving on, we have all disciplines under one roof, like process, mechanical, piping, civil structure, electrical, instrumentation, project and construction management. On the left, you can see a little more detail about each disciplinary works that we do, like process, surge, CFD, equipment selection, sizing, mechanical, tank design, piping, engineering, piping isometrics, piping stress, civil and structure, electrical instrumentation, firefighting. We also help our customers with MR, TP, and VDR. We do a lot of pre-bid engineering support. We do safety studies, HSC, feasibility studies, inspection, and project and construction management. These are some of our clients. We've been working with clients all across the globe for the last 30 years. So we work in Asia, Malaysia, Thailand, Indonesia, Singapore, Middle East, America, Canada, Europe, Australia, all across, and of course, India. We use a ton of softwares to carry out our engineering. So we have softwares under process, electrical, civil, mechanical, instrumentation, piping, and of course, project management. I don't want to get too much into the detail, but if anybody has any queries, they can feel free to ask me. That's about it. Thank you. You may reach out to us at www.pmekng.com or write to us at info@pmekng.com. Moving on, I will hand over the dais to Namita Madam. She is our senior principal process engineer, and she'll take you through the session today.
Hi, good evening all. So, okay, so let's see the attendees, how many we have. We have around, I think, 63 attendees, right? So few of you can introduce yourself just to know like which background the people which we have and what kind of experiences they are having. So those who want to speak can raise their hand so that we can unmute one by one. So Naina Ravi.
Hello.
Yeah, Ninar.
Hello, I am Ravi Sankar from Kothari Sugars, Trichy.
Okay, your voice is not much audible. Okay.
I am Ravi Sankar from Kothari Sugars, Trichy.
Okay. Welcome, Ravi. Which industry you're working?
Sugar industry, madam.
Sugar industry. Okay.
Sugar and power plant.
Okay. Welcome, Ravi. Then
Thank you.
Suresh.
I
Yeah,
am Suresh Muchandan.
yeah.
Can you hear me?
Yeah, I can hear you. Yeah, Suresh.
It's a little faint. Okay, fine. We work for Applied Tech and Management Consultancy, which is basically a consulting company for globally dominant companies in the oil and gas, offshore, and upstream markets.
So where it is based, Clacton?
Yes, I mean, sorry,
Where this company based in?
Bombay. It's based in Bombay. We
Okay.
have a small plant in Gujarat,
Mhm.
and we work a lot with RK Engineering, RK Controls, and I mean, specifically to pressure relieving devices, we have within us the Weir Group, which is Saracen and Sieben, as well as Technical Italy. They all make safety relief, both loaded and pilot operated.
Okay. So we have the people from oil and gas, from sugar industry, anyone from chemical industry who is hardcore working in chemical industry? Just raise hand. Whoever want to speak can just raise hand. Okay, all right. So we'll start our session. So whoever want to interact or ask any question, so in between we can take the question. I'll take a pause wherever you want me to take. So it's 4:38 now. So we have a session till 6 o'clock. So I just want to understand what's your understanding about the pressure relieving devices. I mean, those who are working in industries. So when it comes to pressure relieving devices, so what do people think about it? Yeah, Dada sir.
Yeah, pressure relieving devices, what we understand, it is used in the industry for safeguard our equipment as well as for the personal safety.
Right. So basically, PSV is considered as the ultimate safety of the plant. So I hardly seen any plant where we don't have given the PSVs. So it is considered as the ultimate safety of the plant, and it's a mandatory requirement to provide PSVs on the equipments, on the pipelines, wherever you want to save the system. So let's start our presentation. It's a webinar on pressure relieving devices. So as Lekha already explained about the PMAC values. So the content of the presentation is first we'll see the purpose. So purpose is mainly like we are going to see the PSV which we size in a chemical industries. Okay, but the scenarios which I'm going to discuss, it is like more or less in all the industry it is followed. Maybe few of it is applicable to chemical and few may be applicable to oil and gas. But all the scenario I'm covering here, so whoever from oil and gas and chemical can be correlate with the scenarios. Then there is a definition like MAWP or what is the blowdown or what is the set pressure. So there are some terminologies which we are using in our presentation. So what do you people understand about the MAWP? What is maximum allowable working pressure? Anyone of you? Okay, fine. MAWP is nothing but it's called as a maximum allowable working pressure. So one thing is a design pressure. So based on design pressure, you give this design pressure to mechanical, and mechanical select the thickness of the your vessel, for example. But let's say I have a set design pressure of 60 bar gauge, but the corresponding thickness for that 60 bar gauge is coming something like, let's say 10 mm, but he select 18 mm instead of 10 mm. So whatever the pressure he'll get considering 18 mm, that is called as a maximum allowable working pressure, which is more than your design pressure in this case. So normally this maximum allowable working pressure is equal to your design pressure. It can be more than your design pressure as well, the case which I just explained to you. Then there is a term called blowdown. So blowdown, like all the PSVs, you set at a pressure which is your design pressure. So when you set that design pressure, so when this PSV opens, it start opening at your set pressure. Okay, but once the system is relieved, when it is closed back to its original position, it is not exactly closing to a particular pressure where you have set the PSVs. So there is always a difference between the opening pressure and the closing pressure of the PSV that we call as a blowdown. Then set pressure, as I already said, it's a design pressure. Then a relieving pressure. So basically relieving pressure is the maximum pressure which it can depressurize from your system. Like set pressure is your design pressure. But if you refer API 521, you will see there are different types of PSVs are given. Conventional, pilot operated, balance belows. So they have a range based on the single PSVs, multiple PSVs, the PSV which you're sizing for a fire case, non-fire case. So there are the percent overpressure is mentioned in API 521. So let's say I am designing for non-fire case. So API 521 says, like if your design pressure, let's say 10 bar gauge. So for non-fire case, my overpressure will be 110% of your design pressure. So 110% means it's a 11 bar gauge. Okay. So that is the maximum pressure which your PSV can be relieved. So it will start opening from 10 bar gauge, but full opening will be at the 11 bar gauge. So that's a relieving pressure. Okay. Then we'll see what are the different types of pressure relief devices. Then we will see what is the installation and location of pressure relief valve. So if you have to give the pressure relief valve on the equipment, so where you should install that. So that we will cover in this. Then the configuration of pressure relief inlet and outlet lines, like what walls or vent drain arrangement and all that things, what you have to provide. Then standard pressure relief valve sizes. So basically API 526 we use for the standard relief sizes. There is a table is mentioned. So from that we'll come to know it starts from D orifice and ends with T orifice. So all the sizes are given there. Let me tell you, there are three important APIs. So API 520, 521 and 526. So basically API 520 we are using for the sizing and the installations of PSVs. So there is part 1 and part 2 of API 520. API 521 we are using for the relieving scenarios. So we will going to cover all the relieving scenarios, but these all are referred from API 521. So it's given in a very detailed way in the API 521. And once you, the steps of PSV sizing, it's like, first you envisage the requirement of the PSV for your system. So once you identify the requirement, then you will see where to install. And once you identify the scenario, then you have to do the sizing. So for sizing, you use API 520. Once you sizing means you calculate the area for the orifice area of the PSVs. So let's say from my calculation, my sizing, let's say 10 mm square as per API 520. Then I'll go API 526 to refer the table where the orifice sizes are given from D orifice to T orifice. D is the lowest size there. So I will see for my calculated area, which is the nearest area there. And accordingly, I will select the type of the orifice, I mean the size of the orifice. So that is the given in API 526. Then then relief scenarios. So as I said, it's in API 521. You will find all the scenarios, but we are going to discuss about that as well. Then what are the input required? So for PSV sizing, what are the input requirements? Then what are your process engineering deliverables for that? Then what are the applicable standard and practices? So as I said, there are mainly 3 APIs, which I just mentioned now. But if you are working on a Shell-based project, so Shell always emphasize to use their own standards. So Shell have their own standards. So that time that Shell standards has to be referred. Then some ASMEs for non-API PSVs. You can refer ASMEs, and especially for boilers. So we can use ASMEs. Then API standard versus design pressure of equipment. So we'll see here what are the different design pressures for different equipments, and what is the criteria of selection of it, and the relation between the events. So in this we'll cover as I said, there are the different scenarios, around 20 plus scenarios are given in API 521. So like sometimes it happen, there is a sequential scenarios or some simultaneous scenarios. For example, if the overall plant shutdown, so overall plant shutdown, if it is happened, so what happens? So whatever electric driven equipment in your plant will stop working, right? So once it stops working, then you have to see what is the consequences of that. So it can be a sequential, it can be simultaneous, but forcefully you need not to consider 2 scenarios at a time because it's called a double jeopardy. And API 521 is not allowed for double jeopardy until and unless it's a common cause like total power failure or your utility failure. So that time you can consider this sequential or simultaneous kind of scenarios. Okay, so basically, as I explained already, the overpressure criteria to be considered. So if you refer this table, so this table is from API 520. So if you see the first relief devices. Okay, one more thing I would like to say, like from my calculation, the required orifice sizes, which I'm calculating, if one orifice is not sufficient, let's say the maximum size which is given in API 526 is T orifice. So if I use the T orifice, but still there is an additional area required for my scenario, then I have to use 2 orifice. That may be lesser than T, but maybe 2 R type of orifice or any other F type of orifice. So here is a criteria given for the single device installation and multiple device installation. So what it says, like if you have a 2 orifices, it's normally 2 working, 1 standby. So what will be the set pressure and relieving pressure for first orifice? And what will be the set pressure and relieving for the second PSV? So this table is telling about that also. So if you see the first relief device, its maximum set pressure is 100% of your design pressure. So let's take design pressure as a 10 bar gauge. So your first relief device is set at 10 bar gauge and maximum accumulated pressure. And this is for non-fire case. If you see for non-fire case, the maximum accumulated is 10% above your design pressure. So here my set pressure is 10 bar gauge, but my relieving pressure will be 11 bar gauge. Okay. So if I have a multiple PSVs, let's say I have a 2 PSV. So my first PSV set pressure will be 100. So which is 10 bar gauge, and my additional PSV is set at 105% of 10 bar gauge. And in that case, my relieving pressure will more than my single PSV case. Now for single PSV case, it's 110%. But for my multiple device installation, it will be 116%. Now talking about the fire case, whether it's a single PSV or multiple PSV, your relieving pressure will be 121%. And your set pressure is again the same criteria as that of non-fire case. And here he has given another third PSV also. So the set pressure of third PSV will be 110% in this case. So as I explained you the blow down, so basically blow down is the difference between the PSV which is opening and the closing. So sometime wherever you set the pressure, it is not happening that once it is relieved. So when it close, it is exactly close to that set pressure. So the difference between the opening and closing of the pressure is called a blow down. So chattering. So chattering is a very famous phenomena in industry. Chattering is something happen when there are the three causes. If you see, first is the excessive inlet pressure drop. So excessive inlet pressure drop, if you see this cage, you can see there is a multiple loops in the inlet of your PSVs. So because of that, a lot of pressure drop is happening in your PSV inlet. So normally API 520 is not allowing more than 3% of your set pressure. But still, if there is an excessive inlet pressure drop, so chattering can open. So what is chattering? It's an on-off of your PSV. I mean, your PSV keep on and off. So that's called a chattering. And the another is the excessive buildup back pressure. So what is buildup back pressure? That the PSV, I'll just draw. Okay. So let me, this is a PSV and this is a relieving. Okay. So this is the inlet to PSV and this is a relieving to the relief of the PSV. Okay. So whatever the back pressure experiencing here because of your downstream system. So it's called a back pressure to your PSV. So basically, if you have an excessive buildup back pressure, so that also causes the chattering of your PSV. And then the third one is a oversize. Oversize in the sense, let's say from my calculation, the required is D type of orifice. But if I selected E type or F type, which is higher size of than what I required, so that time also chattering will happen. So normally this oversize valve is, I'll show you a case where you can see the oversizes happen. Like, see, I have a 3 scenarios applicable to this PSV. So here one is the loss of steam, which required 20,000. Then loss of power scenario required a 50,000 lbs per hour, and loss of cooling scenario required 1 lakh lbs per hour. So now, if I the example where I have selected a single PSV of a capacity of 120 lbs per hour. So what happened for loss of cooling, it is adequate. But when when it is go for loss of power or loss of steam, it is highly designed. I mean, there is a lot of design margin. Whatever is required. So in this case, that chattering will happen. So what is the solution to it? You can give a 2 small PSVs. See here, I have given 2 PSV. One is set at the 30,000 lbs per hour and another at 75,000. So in this way, when loss of steam happens, so this PSV can cater. And even if you see the set pressure of 301 PSC, I set at 300, whereas this PSV 300, I set at 315, which is more than this. So first, whenever loss of steam happens, first this PSV will open. And loss of power, both the PSVs will open because the pressure is keep on rising. So first 301 will relieve and then 300 will start when 315 reaches. So pressure relieving devices, sometimes you heard like pressure relieving devices, people call also pressure safety valves also. So the terminologies is only different. I mean, it's based on the type of the fluid which you're relieving. If you're relieving the liquid, which is an incompressible flow, then it's called the pressure relief valve. And when you are relieving the compressible fluid, it's called the pressure safety valve. So that is only the difference between these two terminology. Otherwise, the sizing and all other scenario consideration is same. So along with pressure safety valve, there is another device called the rupture disc. So I will show you a table where you can like get a good idea about it, that these pressure relief devices are categorized closing and non-reclosing. So basically closing is like in case of PSV, like once it is popped, it will close to its original position. But in non-reclosing, once it pop, it get bricked. So it like you have to replace that device. So that is the difference between closing and non-reclosing. So in closing, you will see the spring loaded and again pilot operated. So in spring loaded, we have a type conventional and this below type. So you will see based on if you have the 10% this back pressure to set pressure ratio. So you go with conventional type. And if you see the back pressure to set pressure ratio is 30 to 50%, you will go below type. And if your back pressure to set pressure is more than 50%, so you go with pilot operated type PSVs. So again, in pilot operate, you can see it's a pop action or modulating action. So in pop action also, it's a flowing and non-flowing, and modulating it is flowing and non-flowing. So I'll show what is the difference between flowing and non-flowing. The non-reclosing, it's categorized again in buckling pin or rupture disc. So it is like permanent damage of the device. Once it's popped, it permanently damaged, you have to replace it. So either you can use a rupture disc or you can use a buckling pin. So it's a typical conventional pressure relief valve. So as I said, when the back pressure to set pressure ratio is 10%, less than 10%, then you go with this type of valve. So if you see the advantages, it's most reliable type if properly sized and operated. Versatile, can be used in many services. It is used the places where it is open to atmosphere, maximum cases like for steam, water, air services. And the disadvantage is relieving pressure affected by back pressure because this spring which is set here. So normally it is affected by the back pressure which is experiencing on this PSVs. So it is highly sensitive to the back pressure. The example which I say, let's say my set pressure is 10 bar gauge. Okay. And my back pressure, let's say it is 0.1 bar gauge. Okay. 0.1 bar gauge here. So my PSV will never open at 10. It will always open at 10.1. So that is because of the back pressure which is experiencing on the spring. So that pressure only it will open. So this spring can be manually adjusted to that pressure so that it can save your system. So that is one of the disadvantage of the conventional type, and susceptible to chatter if builder back pressure is too high. So we already seen what is chatter. Then balance type, as I said, when the back pressure to set pressure ratio is 30 to 50%, so we go with balance type of PSVs. They have a lot of good advantages, like you can use in a corrosive service because the bellows which you have used, you can isolate this valve internal from corrosive dirty fluid. So that is the advantage. Then when you have a higher viscosity greater than 20 cp, and you should avoid using it in a heavy oil, waxes, solid services, and cooking because it can choke the bellows, and freezing also may occur where you are expecting the hydrate kind of services. Similarly, for pilot also, you have to avoid these services because it will choke basically this PSVs. So advantage of the this balance bellows is relieving pressure not affected by back pressure, which was conventional was affecting. So that was not the case in the balance below. So when you are in doubt, like initial sizing, when you really don't know what exact the back pressure, so it always better to go with the balance type because it is not much affected and you have a lot of range between 30 to 50% ratio. So it's better to take balance below, though it is a costlier than conventional one, but you will be always in a safe position. It can handle higher buildup back pressure. It protects spring from corrosion because this below can isolate your system. The disadvantage, below susceptible to fatigue and rupture. So that is a disadvantage of it. May release flammable toxic to atmosphere and require separate venting system. You will see there is an additional vent given to balance below. So pilot operated, this is the costliest among all three. So pilot operated, when you have the back pressure to set pressure more than 50%. So you will see there is one valve called pilot valve here, and here is a main valve. So basically normal condition, your pilot is always experiencing the pressure same as that your normal operating pressure of your system. So once the pressure started increasing here and reached the set pressure, So basically, during normal operation, the flow is like this. I mean, it's going to a pilot and then it is going to a dome. This is called a dome here. Okay. So basically, it is balancing. Your pilot is balancing this valve. But once the pressure is keep on increasing, so what happened? The fluid in this dome, went out, and then this valve is started opening, and then this is the outlet. So this way, this pilot operator work. So advantage is like relieving pressure is not affected by back pressure, can operate up to 98% of set pressure, less susceptible to chatter. Disadvantage is pilot is susceptible to plugging, limited chemical and high temperature use, and then vapor condensation and liquid accumulation above the piston may cause problems, and potential for black flow. So these are the advantages of pilot operator. So rupture disc is like it's a non-reclosing type of equipment. So mainly we'll go with rupture disc when the fluid is corrosive. So you don't want your PSV corrosive or high temperature service. So mainly in that scenario we use a rupture disc. Sometimes you give the rupture disc in combination with a PSV because rupture disc is not considered a reliable safety for your system. So these are the different types of rupture discs available in the market. It's a forward acting, reverse acting, and graphite shear loaded. Here's another non-reclosing type. It's a pin actuated devices. So here you can see a buckling pin here. So like it's a normal position, but once the pressure is relieved, the pin is get buckled, and then you have to replace this pin. So now the installation of the PSVs. So basically first let's start with the vessel. So on vessel, when you have the PSV, so if you have the demister pad here, so it's always install the PSV upstream of the demister pad. Because the reason is like if it is get blocked, so it will not relieve the flow through this. So that is a good location of PSV. Then if you talk about the filter, again, in filter also you will experience the same thing because filter can also choke. So it is better to give always a PSV upstream of filter. For column, normally you will see the PSV on the column overhead. And this line normally goes to a condenser cooler basically, and then condenser. So many a times you can use a common PSV for condenser and column as a common PSV. And if you want to give a separate PSV for column and separate for this condenser, then you size this PSV, condenser PSV only for fire case. Then talking about the reciprocating equipment, whether it's a reciprocating pump or compressor. So it is always at the downstream of your discharge side, because reciprocating is having a tendency of increasing the pressure to the infinite curve. So that's why this PSV by default we are given, whether it's a pump or it's a compressor, we always have a PSVs. On heat exchanger, you will see there are three scenarios where we give the one is like a like in your heat exchanger. This is inlet. So let's say this is hot side and this is cold side system. So cold side, if it is blocked in and hot side is still running, so because of this heat transfer, so there's a temperature rise happen on the cold side. So you need to give a PSV. It is called as a thermal safety valve also. There are some cases where your cold side and hot side, normally the as per ASME it is 10/13 the rule should be there. I mean your higher pressure design pressure let's say it's a 10 bar gauge. So your lower pressure design pressure minimum should be 10/13 time of 10. So if you're designing by 10/13 rule, then PSV is not required for heat exchanger. Similarly for fired heater, so for fired heater also, if you see the location, so basically in case of fired heater, people don't normally prefer giving the PSV. The reason is that for fired heater, the outlet temperature is too high and relieving that high temperature fluid is a problem. So normally people give a PSV at the upstream of the fired heater. But still, there is a lot of mitigations are given, like you can give the different transmitters here, pressure and temperature, just to mitigate, to avoid this PSV on this fired heater. Okay, so relief valve configuration, if you see, like this is relief valve, so inlet and outlet. So you will have a block valve. So both the side you will have a block valve. You will have a drain at the upstream and vent at downstream. Then you will have the spool piece here at the flange and expander reducer on upstream and downstream of PSV. So here reducer and here it's a expander. So that's a typical configuration of the PSV. Okay, relief valve bypass, it's like when you want to do the manual depressurization of your system. Normally there are the BDVs are given to automatic depressurization to the system. So whenever you want to do a manual depressurization, so you will give a PSV bypass. So it can be it normally be a globe valve. So you can just throttle it manually and depressurize your system. So as I said, there's a standard pressure relief valve sizes which are available in API 526, which will helpful after calculating the orifice sizes as per API 520. You can refer this table. There are also some scenarios where you use a non-API valves. So that's a vendor specific. So the services like chemical injection, chemical injection pump, thermal relief valves and piping, you use the non-API pumps, non-API PSVs. Relief scenario, so here a total 23 I have listed, so it is as per API 521. So you will see the different relieving scenarios like fire liquid vaporization case. So let's say I'm having a liquid fill, I am having a vessel filled with liquid. So your vessel is filled with liquid and it will catch fire. So whatever liquid inside your a vessel, it started vaporizing. So that is a fire liquid vaporization case. Similarly, if your vessel is the gas filled vessel, so that time it's a fire gas expansion case. So you have to size your PSV for only gas relief, for gas expansion case. Then blocked outlet is something, let's say I have a vessel and I have, this is inlet line, this is outlet line, vapor outlet line, and this is liquid outlet line. So on both the, let's say I have a valve on both the side. So if this valve get blocked, so I can say it's a vapor blocked outlet. If this valve get blocked, then I can say it's a liquid blocked outlet. So in blocked outlet, you can size this for vapor and liquid accordingly. Then control valve failure case. So inlet, if you have a control valve here, so sometime or many times we give a bypass because for the operation of this control valve. So if your control valves get failed, so fail means it's a full opening of your this control valve, normal control valve. So what happened, whatever the normal pressure flow rate, let's say it coming X, it can be full open maybe 2X. So the 2X start pressurizing your system. So you have to relieve that pressure by using the PSV. So that you will cover in a control valve failure case. Then for heat exchanger, I already told you, like if you're designed by 10/13 rule, so PSV on that is not required. The case of thermal, TSV can be provided on the cooling side. And also, if your downstream is not designed for that much of pressure, that case you can give a PSV for heat exchanger. Relief calculation for that fractional column. So in fractional column, you will find lot of scenarios. Actually, the column is one of the critical PSV calculation considered in industry, because it almost cover all the scenarios required. So here, if you see it's a vapor outlet, so you have a cooler and going to a condenser. You have a reboiler here. This is liquid outlet. So it's your inlet line. And sometime you might have a side stream as a reflux. So one is reflux, normal reflux, but sometimes you have a side stream also. So here, like all the scenarios are applicable, like vapor blocked outlet, liquid blocked outlet, control valve failure, because if you have the normal like inlet control valve here, so control valve failure, fire case, then your total power failure. So in total power failure, normally here we give a pump, so which caters to your column as a reflux. So this pump gate fails. Even to a reboiler, you are getting the flow through a pump, which is hot oil pump. So that pump gate fails. So total power failure. Then if you there is a partial power failure also. So partial power failure, it is something you in your plant you have the different substations. So in partial power failure, you consider a particular substation which is fed, not all substation at a time. So that comes under the partial power failure. Then utility failure. So here, as I said, hot oil you are using. So hot oil failure is one of the utility failure case. Here, if this is cooler, it's a cooling water supply. So you can consider the cooling water failure case. And an instrument air failure. So instrument air failure, it is something that your whole plant will be shut down until unless you have a backup to your instrument air compressor. And I mean, if you're not at all having instrument air in your system, the whole plant will be shut down and everything will be depressurized to flare. So, okay, so it's a control valve relief heat exchanger fractionation column. Check valve failure case. So let's say you have a pump. So at the downstream of it, you have a check valve. So basically, it's a high pressure system, and at upstream, you have a low pressure system. So definitely, if this check valve, normally it will not allow backflow, but when it's leakage, so what happens? Will be some backflow to your low pressure system, and it will start pressurizing your low pressure system. So there you provide a PSV just to safeguard the low pressure system from high pressure system. It can also be a case for compressor because there also similar arrangement is there. Then thermal expansion, as I said, it's a long pipeline. Like because of solar radiation, if this valve is blocked in on both the side, then because of solar radiation itself, there should be a expansion of the liquid fluid. So thermal expansion is applicable to that. So utility failure we covered. Partial failure, it's a power, that also we covered. Then failure of absorbent medium. So it is something like you have absorber column. So like you have to envisage the scenario if your absorbent is failed. So what happens? So basically, normally whatever gas is coming to your column is getting absorbed by this your absorbent. So in case of absorbent failure, it is not getting absorbed and only vapor is coming and that start pressurizing your system. So that is a credible scenario for this. Then accumulation of non-condensable. So let's say this example, when you're cooling, this cooling water fails, or maybe air cooler if it is there. So if your electric power fails, so that case your cooler is not working. So there is a lot of accumulation of non-condensable. So you have a lot of vapors here. So that also start pressurizing your system. So that is the scenario. Then entry of volatile material. So as I give you example of the fired heater. So fired heater, normally you have a hot oil as a fluid, but sometimes this hot oil also get condensed. So some water comes into it, or maybe contamination by some light oil, hydrocarbon of your plant. So what happened in this case, when that fluid enter to this fire heater, so along with your hot oil, basically water and light hydrocarbons have tendency to vaporize first. So a lot of vapor get generated. So that is this scenario. Then liquid overfill. So like control valve failure case, as we discussed earlier. So let's say this is my vessel, and this is inlet, and this is a liquid outlet line. So by any means, if this liquid outlet line, if it is blocked by any means, okay. So what happened? The incoming flow is still there. So there is a liquid flow rate, or it's a two-phase. So incoming flow is still coming. Your vapor are allowing to go outside, but your liquid is not passing. So what happened? Your level is keep on building. So what happened? It can reach to a level and it can overfill your vessel. So that is the scenario of liquid overfill over here. Then liquid failure, for automatic control. So automatic control, it is nothing but all the control valves which you are given in the plant. So you have to analyze one by one, like pressure control valve, temperature control valve, and level control valve. So what kind of consequences of those failures, you have to analyze those one by one in this scenario. Then abnormal process heat or vapor input. So you can see loss of heat to this reboiler in the column case. So it can gain this because hot oil is still coming. So that is basically your abnormal process heat or vapor input. Then relief load calculation for turbo expander. So normally the people who work in oil and gas, they know this turbo expander, which normally use in bypass to turbo expander JT valve is given. So this relief scenario is only dedicated to that turbo expander. Then cooling or reflux failure. So it is again similar to this, because this cooling is not happening. So you're not getting any reflux to your column. So this is that scenario. Then internal explosion. So basically, let's say I have a tank and the service, and my vent is open to atmosphere. So maybe the fluid which I stored in a tank is having a tendency to form an explosive mixture with air. So that is the scenario which you have to consider in a internal explosion. Then chemical reaction. So the people who are working in the chemical industry, so we deal with the reactor. So normally all the parameters like temperature, pressure are maintained in the reactor, but because of any composition or any reagents, maybe any uncontrolled reaction happen. So that time also the pressure can be, pressure of your reactor will increase. So you have to give one PSP on this reactor to save your reactor. Then hydraulic expansion, we already discussed, like if I have a long pipeline, let's say, and I have a block valve, both the side. So because of solar radiation itself, it can expand. So we give a thermal relief valve here on liquid lines. Similar for gas line also we give, and that time we call it a PSV. And for liquid, we call it a TSV. Then overpressure prevention during maintenance. So like during maintenance also you can experience some overpressure because of mismanagement of maintenance activity. So that also you have to consider here. I hope these all scenarios are covered and cleared. Okay, so we covered all the scenarios. So it's all the same description which we discussed just now. So in utility failure, you will see one by one, there is a lot of utilities and the parameters which you have to consider. Okay, so now particularly talking about the storage tank. So normally in storage tank, like if it is a water line, I mean, it can be a water tank or it can be sometimes dome shaped, sometimes it's a cone type floating roof based on whatever the service you are giving. So here you will see we provide the breather valves, which is basically in breathing and out breathing can be performed through the same valve, and then we give the ERVs, emergency relief valves. So basically, these breather valves are sized based on the pump in and pump out flow rate. So the out breathing flow rate is considered by pump in plus there is any expansion in your because of thermal. So API 2000 is used for the venting calculation of storage tank. So here you estimate this out breathing flow rate, and similarly for in breathing flow rate, your pump in flow rate plus the thermal effect. So that will give you the out breathing flow rate. And emergency relief valve is something you use only for fire. So whenever there is a fire happens, so there is in API 2000, all the detailed calculations are provided how to estimate the fire load. So what are the input required? So basically you require a PFD first to understand the system, and then understand the system and then identify the location of the PSPs where you have to provide to safeguard the system individually. Then you need a simulation for all the properties. But always keep in mind, whenever you size the PSP, you have to estimate the properties at the relieving conditions. So simulation through you get a heat and mass balance. Then in PNIDs, because just to do the detailing of that PSPs. Then process and mechanical data sheet. And what are your deliverable? It's like relief and blowdown summary is a document which normally we prepared plant-wide, where we listed all the PSVs or BDVs, which are blowdown valves in your system. So that is one of the deliverable. In design basis also, you give a brief about your relieving conditions or requirements. And there is a process design criteria also given. Then formal calculation of each relief devices. Then process data sheet of all disposal, blowdown and vapor depressing equipment. PFD for all equipment. And this is something you give only if you use if you performing the shell based project, because the process safeguarding flow scheme or process safeguarding memorandum is only asked by shell client. These are the standards as like few of important one I already mentioned. So these are all API standards. Then few are ASME. So basically for boiler and pressure vessel, we use ASME standards. Then are some shale DP. So as I said, if it is a shale based project, so you have to refer shale standards and some other references. So basically, if you refer API 520, so you will see there are different scenarios given for vapor release, liquid release. So vapor also they categorize critical, non-critical, supercritical. In liquid, you can say they have categorized certification required, non-certification required. So this is a very good paper for the relieving for supercritical fluids. So you can refer this, is available online, I think. Then size depression relay device segment exposed to fire. So this is again another good paper. And then calculating column relief load. So basically, as I said, column relief load, it is one of the crucial, complicated one considered in industry because it is all the relieving scenarios are applicable to the column. So in column, you will see there are 3 methods given to estimate the column relief load. So one is called the unbalanced heat load method. So unbalanced heat load method, what you do, you will do the enthalpy balance across the column and identify the relieving load. So based on your feed enthalpy, your condenser duty and condenser enthalpy, and your reboiler duty and reboiler enthalpy. So you estimate the relief load, and it's a very preliminary and crude method used for column sizing. But if you find that if your relieving load is coming very higher, your flare sizing is going very high, then people go with the dynamic simulation of it, because dynamic simulation gives the precise flow rate, and it's reduced one also compared to the conventional method. So here is a very good paper also for the same column. So it is talking about that dynamic simulation techniques. Relation between events. So as I said, the events can be simultaneous, can be sequential, or can be individual based on what type of scenario is applicable to that equipment. So as I said, again, let's take an example of vessel. So here you can say sequential scenario can also be happen. So how I will just tell you. So it's a vapor outlet, it's a liquid outlet, and it's a feed coming to your system. So here is a control valve. Okay. So let's say if my control valve fails, okay, it's an individual scenario, right? Nothing is affecting because of this control valve failure. If my vapor blocked in, it's only vapor blocked in because my liquid is normally flowing outside of it. But let's say my vapor is going to a compressor. Here downstream of vapor, I have given a compressor. Okay. So now imagine a scenario where you have a liquid blocked in. So when your liquid blocked in, I mean the flow is not passing through the liquid line. So what happened? Your level keep on increasing. So when it is reaches to high liquid level, okay, when it reaches to high liquid level, what happened? Your compressor trips, because you will not allow vapor to enter in your compressor. It will damage the compressor. So ultimately it will become your vapor blocked in also. So in this scenario, it's a sequential event. You have a liquid blocked in, and at this, I mean, after some time, you will have a vapor blocked in also. Okay, so that's all. If you have any question, we can take it.
Yeah, thank you, Namit. There was one question, I think, in the chat box from Saman. He's asking whether can relief pressure be more than MAWP?
No, actually, because MAWP is your maximum pressure which your equipment can handle. So it cannot be more than that.
Shanari madam, you want to ask something?
Yes. Are you audible, ma'am?
Yeah, you're audible. Yeah.
Suppose in PSV calculation, if I'm getting D orifice and the client want E orifice, so that time what to do?
You can go with E orifice because there are some client who in the beginning of the project give the list of the type of orifice which you have to go with. So like in that list, if D orifice it's not there, then definitely you have to select E orifice. But you have to take a confirmation from the vendor whether this chattering is happening or not for that selection.
Okay. So it depends upon chattering.
Yeah, because your the required orifice area versus the selected should not be much higher. There should not be much higher gap between these two areas.
Okay, ma'am. And second question is how to calculate the relieving temperature if I'm not having relieving temperature. So at that time, how to calculate the relieving temperature?
One is simple ideal gas equation PV equal to nRT, with that you can calculate.
Okay.
Another, you can use HYSYS also. You can put a pressure as your relieving pressure, and corresponding to that relieving pressure, you will get relieving temperature.
And the last question is that suppose I'm having one column and in the column I'm having one PSV. So the case will be power failure case in column. So at that time, how to calculate the relief load?
Yeah, as I said, you power failure, you have to see whatever the equipments we are catering to your column. For example, reflux pump, which is sending reflux to your column. Or
Okay.
at the bottom, your bottom maybe product or feed pump if you have, or maybe feed pump if you have, which is coming to your column. So
Okay.
you have to identify if it is a total power failure. So you have to consider all the equipment which are electric driven coming to your column. That failure you have considered, and you have to consider the total load for that PSV sizing.
Okay, ma'am. Thank you so much.
Yeah, John, you have some question? Yeah, John, I think you have some question.
Hello.
Yeah, hello, Dhruv.
Can
Yeah,
you hear me?
yeah, I can. Yeah.
It's actually this Dhruv this side from RK Controls. I just want to know the ma'am setup for arranging or setting up pressure safety valve in combination with rupture disc.
Hmm.
What's the set pressure? Are we going to set the same pressure for both rupture disc and safety
Yeah,
valve,
yeah,
or
both
what?
same pressure, same pressure.
Same pressure. But usually in industry, what I have seen, ma'am, that they are installing rupture disc at lower pressure and safety valve at higher pressure. Is it a good practice?
You can, because rupture disc is the first device which exposure to your relieving fluid. So first your disc will rupture and then PSV will experience that. So in that you can, I mean, set the rupture disc at lower pressure than PSV. But a good practice is like, I feel both should be at the same pressure. That should be a good one.
Or can we arrange that? Can we arrange or mount both the rupture disc and safety valve on the same port or on different port? What
Normally on the same platform.
at the same at the same nozzle? I'm saying
Yeah, it is on the same nozzle.
on the same nozzle.
The line which is coming out from your nozzle. So first you will install rupture disc, and outlet of rupture disc you will install PSV.
So what will be the benefit if, let's say, rupture disc get ruptured, then I have to dismantle my pressure safety valve and then I have to replace that rupture disc, and then I'll have to do the reinstallation of safety valve and new rupture disc. So I just want to know, is it a good practice to mount these two at separate nozzles or at a single nozzle? Because I don't find any benefit to install both these at same nozzle.
No, see, first of all, the intention you have to understand why you are giving rupture disc in combination of PSV. Because you are handling the corrosive fluid or you are handling the high temperature fluid, which you don't want your PSV to expose all the time. So you are giving a rupture disc in between. Okay. So,
Okay.
and normally we have a good engineering practice, like we always have a standard PSV, standby PSV. So the complete arrangement, you will have a standby also. So once your first PSV is, I mean, rupture disc break and PSV relieve that relieving load. So always there is one standby PSV on that. And when you want to dismantle that ruptured disc, which one is ruptured, so you can take that into maintenance by just closing the isolation valves, inlet and outlet to that. And you already have one standby PSV and ruptured disc to the system.
Okay, ma'am. Got it.
There are a couple of questions. I'll just read them out on the chat box. Will the back pressure affect PSV if pilot discharge to some flare header, to the same flare header as main process fluid discharge?
Normally, main process fluid discharge is not discharged to flare. The lines which are connected to flare is only to the safeguard your system for depressurizing or for PSV relieving. So your normal operating line are not connected to the flare. Only a scenario where you have a pressure control valve on your, let's say, vessel, you have a pressure control valve, and you're setting your vessel, let's say 10 bar gauge. Any moment, if the pressure exceed to 11 bar gauge, I don't want my PSV to pop and relieve all the inventory to the flare, because that is a wastage of my product. So that case, I will prefer to give a pressure control valve, which will just modulate my pressure to operating pressure, and a little amount will discharge to flare.
Right. Another one is, what is recommended blowdown in PSV? Does it vary for different equipment?
See, blowdown is a separate equipment than PSV. There is a different calculations required for blowdown. But there is a one scenario called fire where the blowdown valves and the PSV can both open at the same time. So there is a separate study required for blowdown. May I answer your question?
Okay, I'm going to unmute Naina now. Could you please unmute?
I think Nainar having some issue at his end.
Maybe I can unmute. Yeah.
Hello, ma'am. That my question was regarding that POSV, pilot operated safety valve. Yeah, in that POSV, I have seen in our plant that that pilot discharge and the main process PSV discharge both are connected to flare header, and both are actually that very nearby to each other. So that you said that if suppose we use a pilot operated safety valve, that back pressure won't be affected because of there is a separate pilot valve. So if that in a case which I have seen, that pilot valve discharge is also connected to flare header, so that suppose if PSV pops.
Your question is
Pops up.
pilot operated PSV, definitely it will discharge to your flare header. But you are saying your process line also connecting to a flare header, right? That is what your question.
No, that my question is that the main process, main PSV discharge is connected to flare header. That is a common practice. And that pilot discharge is also connected to.
Flare. Pilot is also to the flare because it's a type of the
So,
PSV which you're using.
yeah, exactly. So that how that back pressure won't affect that opening of pilot, because that if there is a pilot is like normal PSV only. No?
Yeah, I mean both will open at the same time. When main valve is open, your pilot will also be in open condition.
Okay, so after main valve open, there is a back pressure will available, so that it will affect. Okay.
Yeah, and back pressure will be on the main valve.
Yeah, but like it's a common flare header, so that and that nozzle of discharge.
Yes, Saman, just understand. It's just a type of the PSV. They are not two separate valves. Basically, it's a pilot operated. The construction or arrangement it is like that, but they're not separate from each other. They are the single entity, and they're discharging to a common flare header.
Yes, exactly. So that pilot will only work as a normal PSV only, that spring loaded type.
Pilot, what is the advantage of it? It is providing a pressure on your main valve. So normally your main valve is not open. It will open when your back pressure to set pressure in the range of 50 to 70%. That is the advantage you're getting by using pilot.
Yeah, so that my question is, suppose if main valve open after pilot, that back pressure will affect the operating of pilot then?
See, they are all the same arrangement. I showed you a sketch, right? Okay, let me again go to that sketch. See, they are a one entity, right? They're not separate from each other.
Yes, that is right.
Arrangement is one. So it is not like pilot is discharging separately and main valve. No, both of them are connected to, this is the outlet line. The blue one which you can see is the outlet line.
Yeah, but this is the normal scenario when PSV is not like popped up.
No,
but when
outlet flow when your PSV pop up, right? Normally there is no flow in this blue line.
Yes.
Right.
In yeah, but then what is in this diagram, there is not shown that discharge of pilot valve.
That is what I'm saying. It is not discharging separately. They are one arrangement. This is a one discharge, which is the blue line, which you can see.
Okay.
Okay.
Yeah.
There's a question in Q&A by Anand. Can we use one pilot modulating instead of two small conventional valves to manage capacity?
No, see, the type of PSV is not based on capacity. It's based on your back pressure to set pressure. So if your back pressure to set pressure ratio less than 10%, you go with conventional. If you're not getting that, and if it is 50 to more than 50%, you have to go with pilot operated. And pilot operated are costlier than conventional. So you try to fit into conventional first. But if you're not getting that back pressure ratio, you don't have any other solution to go with billows or pilot operated.
Right. So I'll unmute Mr. Deepak now. Mr.
No,
Deepak?
ma'am, thank you.
Yeah.
My concern is clear now. No, it's
Okay, thank you. Thank you.
Okay, there's one question by Mr. Sumit on the chat box. He's asking your suggestion for a fresher chemical engineer who wants to make a career in process engineering.
It's a very good choice to make a career in process engineer because you will see you are not only focusing on process but also other discipline as well. And if you join a process focused core companies, it is always a very good. And if you see the number of colleges also for chemical engineering are very less. So it's always a good choice to go with process engineering career. Don't go IT and all that after doing chemical.
Okay, there's a question. Okay, I'm going to unmute Mr. Deepak again.
Sorry, this is Dhruv again. Actually, ma'am, there might be some glitch. He's not showing, the system is not showing my name. Dhruv this side. I just want to know, ma'am, I've gone through many refineries and I've found that on tanks there are 2 to 3 relief devices installed on a tank if the capacity is large, like 200 KL or large volume tanks. So I've seen that there are upstream control valves, safety valves, plus breather valves are installed. So I just want to know the sequence of preference, which valve will open first and which will open at the last for the for relieving.
Okay, so let's say you have a blanketing given to your tank.
Right.
So basically that is the first safeguard to your system. Like if your pressure goes below, then nitrogen comes in. And outlet also you have a control valve on the blanketing and split range kind of arrangement you provided. So that is your first safety of your tank. Second is your breather valves. Okay, and the last one is your emergency relief valve. It also called as a emergency. Sometimes it called emergency hatch. Sometimes it also called as a blow off hatch. Okay, so that is the ultimate safety of the plant. Even if you see the low pressure tank, which design as per API 650. The design pressure is very low. You cannot exceed 0.172 bar gauge for low pressure tanks. So there, like as you see in the pressure vessels or the PSV which we discussed so far, you will have an overpressure of 10% for non-fire case or 21% for fire case. But low pressure tank, you don't allow that even that 10% because the margin between the operating and design is so low that normally the conventional thing is like you set your breather valve at 70 to 80% of your design pressure, emergency hatch or emergency relieving valve at 90% of your design pressure. So none of the valves set at design pressure in case of tank.
Okay, and just want to know about the relief capacity. They are sizing each let's say upstream control valve, breather valve, and safety valve at the same relieving capacities or at the different.
Breather valve, you refer API 2000, you will find there is a lot of equations are given for in-breathing and out-breathing calculation.
Right.
So you arrive at estimate load based on that. For fire case, you have the emergency for ERV. Fire case also equations are given. So you estimate relief load as per that.
Okay, so we have different flow capacities. Okay, thank you, ma'am.
Yeah.
There's a question in Q&A. If BVFA is provided at condenser shell outlet, will there be any need of providing PSV on distillation column, vapor or shell side?
Can you repeat again, Lekha?
If BVFA is provided at condenser shell outlet, will there be any need of providing PSV on distillation column?
You can use the same PSV for distillation column also, but in that case, you have to consider the additional pressure drop of your condenser while setting the designing the pressure of the PSV.
Will this be on the vapor side or the shell side?
See, that condenser, if it is a cooling water side, so we already discussed that is like a thermal safety valve, and it is on the process side, then it's a PSV.
Sachin, your query is answered. What is the selection criteria for governing cases in PSV sizing? I think this is something that you already covered quite in depth. But if you still want to take it.
Okay, so as I listed 20 plus scenarios there, you can refer APA 521. The same all scenarios are given in details. Normally, the industries, we have a Excel sheet where we give the we tick the scenario which is applicable to that PSV. So you have to evaluate each and every scenario given in APA 521, and then you have to come out with the conservative flow rate for your case.
Okay, I'm going to now unmute Mr. Danasai, because he was the one who also asked this question.
Yeah. My question is that basically this is as per relief scenario, as well as whether you need to consider that orifice designation, what orifice designation we are getting after the calculating each and every scenario, and we have to select that highest orifice designation. My question is basically that this is for a mixed flow when there will be liquid and the vapor.
Right. So like if you have a mixed flow, there are two different questions actually. One is if you have a mixed flow, so it is categorized as a two-phase flow. So the sizing criteria for two-phase flow is different than the sizing for vapor or liquid relief load. Secondly, as you're saying, you're experiencing different scenarios. So as I explain you, the case where I am having three relieving scenarios, relieving flow rate, 1,50,000 and 20,000. So though 1 lakh is a conservative one and the orifice size, let's say it's a T type of orifice, but still I cannot use because when other two scenarios were there will be chattering. So I have to give 2 or 3 PSVs of the lower relief load so that all three at a time will take the 1 lakh capacity, and other two maybe one for 20,000, another combinedly for 50,000.
Okay. But what will be the set point for that three? That will be staggered.
That will be staggered. Your first one will be 100% of your design pressure. Second one will be 105% of your design pressure.
Okay. Thank you, Namita.
Yeah.
Okay, this is a continuation of an earlier question on freshers. So as you said, core, Sonali is asking what is the advice for a fresher? How to start with core as chemical engineering without any experience?
Without any experience, I mean, yes, you have to brush up all your basics because practical knowledge, it is something not a rocket science. It's all deal with your basics. So just brush up and make your fundamentals very much strong. That is enough to start a career.
Okay, thank you. There is a question in Q&A by Anand. In which scenario do we use DIERS sizing?
DIERS, right? So DIERS is basically an institute, and this DIERS method is given that is mainly used for two-phase relieving load. So when you're experiencing two-phase in your system, you can use DIERS, and there is other two methods also. One is called HEM, homogeneous equation method, something like that. And another is omega method. So these three can be used for a two-phase relieving scenario.
Okay, I'm going to now unmute Savan.
Yeah, we have 10 minutes, 9 more minutes. So I can take questions.
Yeah, we only have a couple of more to go.
Yeah.
Okay, ma'am. In internal floating group tank, suppose there is a continuous liquid inflow, and by somehow, suppose maybe there is sliding problem or somehow that float doesn't can't may move uplift. So is there any provision for safety of or by overpressuring?
Normally, this like rim vents are given, and even breather valves are also there. But your case,
Yeah, but breather valves it's in above that floating group, but
Yeah.
below floating group there is.
Yeah, that's what I'm saying. That is not capturing the scenario which you are telling, because you are saying your roof is not floating. I mean, it's not uplifting. Maybe there is some mechanical failure or anything in the crank to that roof. So basically, what
Yes,
happens,
exactly.
your level is keep on increasing, right? And even your pressure is also increasing. So that time, like you always have an alarm on your tanks. So operator will take the action. He will stop the flow, incoming flow to the tank in that case.
Pressure will increase because there is a constant volume and continuous liquid inflow.
They will both
But
will
level, yeah, but level won't increase now because there is a floating group is at constant level. It won't uplift. So and otherwise that there is a in normal atmosphere floating group, internal floating group. There is no any
Yeah, level.
pressure.
Yeah, and if it is stuck in between, then your LT may not experience that much of level. But yeah, pressure is there, so pressure will take care of it.
Okay. Yes.
Okay, I'm now unmute Lakshmi. Lakshmi, can you unmute?
Yeah, hi Namita.
Yeah.
Yeah, my name is Lakshmi. I work for Archi Controls. I just want to know, you said for conventional PSVs, you offer for those where the back pressure is like 10% of the set pressure.
Yeah.
And then where the back pressure is 50 to 70% of the set pressure, we have to go for the pilot operated ones.
Yes.
So what happens between the 10 to 40% or 50%? There again,
Balance type, balance below type.
balanced.
Yeah.
Okay.
It is
Fine.
30 to 50%.
30 to 50%.
Yeah.
Okay, so, okay, fine. Thanks.
So that was the last of all the questions. Now I am inviting our founder and MD of PMEC, Mr. Mahesh, to just share a couple of. Yeah.
Can you hear me, Lekha?
Yes, can hear you.
I think it was a wonderful session, and I appreciate all participants having attended it, and Namita, making very detailed and quite simplified, yet simplified explanation on how the whole safety system works. I think it has created immense value for all of us. That is our objective also, and thank you everyone and Archi Controls for organizing this session, and all participants having come and spent your valuable time with us. Thank you very much. Thank you, Namita. Wonderful session.
Thank you, Namita, for a wonderful session, and hope everybody found the presentation useful. And thank you once again for spending your valuable time. And thanks again. And should you have any questions, please do let us know. We'll be more than happy to answer. I will also leave my email as well in the chat. Should you have any questions, you can get in touch with me as well.
Sir, is there any feedback system we have? I mean, we can take a feedback.
Pardon?
Do we have a lot of people have written on the chat box. It was very informative session. Thank you.
All right.
Yeah. If there's anything else, feel free to write to us.
Thank you. Thank you.
Thank you.
Thank you all.
Thank you.
Thank you.